Hello and welcome to TCAT Centaurus video tutorial, Centaurus Structure Editor, Section 4, Generating Meshes. In this video, we will use the structure of the 2D PDSOI device that we have created in the previous episodes, define mesh and strategies for the device, and generate mesh. Different device regions play different roles in determining the device performance, based on materials, doping levels and doping gradients, physical models, and so on. Therefore, meshing strategies for these regions are typically different. In this tutorial, we'll demonstrate the most common meshing strategies. Before we start, we need to check that the exact coordinate mode is turned on and auto region naming mode is turned off. As a first step, let's define mesh controls that are applied to the entire device structure. For that, we define a reference evaluation window which covers the entire device domain. We also give this evaluation window a name to easily identify it. Now we can set mesh controls for the global placement window. We launch the refinement specification dialog. Give refinement a name. In the refinement dialog, select the appropriate placement type. Next, name the refinement definition. Unlike doping profile specifications, where we reuse some of the definitions, the mesh definitions are typically unique. Therefore, we just need to make sure that the name is unique and doesn't override any existing mesh definition. We set maximum and minimum element size and expand the dialog to enter two refinement functions. The first refinement function is based on the value difference of net doping concentration. Here, the value 1 means that if the value difference of two adjacent nodes is greater than one order of magnitude, the program will refine mesh edge until the edge length is smaller than the minimum size. The second refinement function sets the interface mesh refinement at silicon oxide interface. At the interface, the element size is 10 angstrom, and the size is increasing with a factor of 1.5 as mesh moves away from the interface. In addition to refinement evaluation window that allows to restrict refinement to a certain area of the device, or as we have just shown, expand the refinement to the entire device, we can also restrict mesh refinement to a specific area of interest, like material or region. Our next refinement specification will be applied to silicon epi region. When creating the structure, we did not specifically name the regions, so we can query the names in GUI. We can also check the name of the gate oxide region. As you can see, newly defined reference evaluation window blocks the view, so we will not be able to easily find, select, and query the region name. So let's hide it. So for that, you'll go into View, Entity Viewer, find our window, and hide it from the view. Now we can see the structure again. So selector, you want to find body, zoom close to the interface, and right click. So region name for epi and region name for the oxide. Open new refinement specification dialog. Give refinement a name. We used PL epi name for profile definition, so let's use a different name. And set placement type to region. Select epi region name. name refinement definition, and set minimum and maximum size. Here we would like to set fine mesh size in y direction and reduce the minimum element size to ensure proper refinement at the junction. Expand the dialog and add refinement function for value difference of doping concentration. As you can see, there are two refinement functions defined already from previous definition. There's no way we can edit their definition, so let's delete them and define the new refinement functions. Add an interface length based function with the mesh size at the interface of 2 angstrom, an effect of 1.5 using region names for silicon epi layer and gate oxide regions. Next step is to save the model. We'll use SOI FET name. To avoid the need rotating the structure at a later step in Visualizer, we want to save it with the proper coordinate system orientation. So using scheme command at the bottom, we type ste set process up direction z, and enter the command. And now we can build the mesh. The dialog prompts for the file name, so we enter SOI FAT, and at the end of the mesh generation, a visualizer will be launched to show and inspect the structure. Build mesh command saves two files for CentOROS mesh, the mesh command file and the TDR boundary representation of the device. Then it launches CentOROS mesh that generates a volume mesh and saves the TDR file. Let's examine the structure. Mesh is anisotropic with global refinement, ensuring reasonable refinement in the substrate, in the box layer and substrate box interface refinement. The second refinement definition controls the mesh near the junctions and in the channel of the device. This concludes the video. Thank you for watching.